Hello, I'm John.
I'm Gus.
I'm David. And I'm Steven, and we're making an AC circuit video.
Alright, for part one, we're going to go ahead and set up our Multisim circuit, similar to the exercise 6 one, but not identical. First, we're going to select our source. We need an AC power source. We also need a ground. And we have a couple of resistors that we already picked out. Our resistor values are 10k ohm down here. That was at 3.3 and 3.3k ohm here. And now we just need to connect these up like so. This is a series only circuit. We've got nothing at all in parallel. Go ahead and change this around. For ours, we chose 3.4 volts RMS, and we chose a frequency of 500 hertz. And there you have it. That's the circuit.
Alright, so as you can see, we have added our voltage meter across our source to measure the volts, and we've also added a voltage meter across our R2 resistor and our oscilloscope to measure peak to peak and our period. Right now we're running our circuit so we can pull up our data. Right now we're going to demonstrate our peak to peak value. And as you can see, our peak-to-peak voltage is 9.616 volts. And now we're going to measure our period. And as you can see there, it is 2.00 milliseconds. Alright, to calculate our frequency, we're going to go ahead and do 1 divided by 2.00 e to the negative 3, which is 500, and that is our frequency.
As we continue our experiment here, we will now measure the voltage peak to peak for channel B, which gives us a value of 7.228 volts peak to peak, and a voltage RMS of 2.556 volts. The period is 2.00 milliseconds. We're now going to measure the frequency. We're going to take 1 divided by 2.00 milliseconds, which is EE to the negative 3, and that gives us 500 hertz, which is what our input sources.
We've set up the same circuit here on the board. We have a 3.3k ohm resistor here, a 10k ohm resistor. Our function generator is set up across the positive rail and going to ground. Also, we have channel A here for the oscilloscope going to the positive and to the ground. We have channel B hooked up across resistor 2, which is the 10k ohm. And our multimeter is also set up for R2. We just used a wire for proxy. It's also connected to the same common ground. Both of our probes have been inspected and they're both set to the 1x setting. And now we're ready to measure.
With this vertical position, I can change the scale. I can bring the bottom of the waveform to the bottom of the display, and then I can adjust the horizontal position so that I can read along this axis with the dashes the voltage peak to peak. So in an old school calculation, we count divisions. So from bottom to top, we see 2 squares, and our scale for the y-axis is 5 volts. So with 2 squares, or rather 2 divisions times 5 volts per division, that is a 10 That is a 10 volt measurement peak to peak, volts peak to peak. Here we have a multimeter, which is set to volts in AC world, and we're going to measure the root mean square volts is measuring 3.4 volts root mean square, which is consistent with our calculation. 10 volts peak to peak divided by 2 gives the peak voltage, 5 volts peak, and then times 0.707 will give root mean square volts, 3.535. Consistent because our method was old school, we have small error. So to measure the period, I've done some things here where I adjusted the vertical scale to get a nice image of the waveform, and I've adjusted the horizontal scale so that we see one complete cycle from peak to peak. I can also adjust vertical to center my vertical. Now I'll go to the positive 0 where it crosses from negative to positive on the left side of the window. Counting divisions will give me my period when I multiply by the units for the division, so 1 division 2. It's 10 divisions. We see 10 divisions left to right along the x-axis, and our unit for the x-axis is 200 microseconds, which is 10 to the negative 6 seconds. 10 divisions times 200 microseconds, and micro is a metric prefix 10 to the negative 6. This will give us our period, which is 2 1,000ths of a second, 2 milliseconds. From this we can obtain the frequency by taking the multiplicative inverse. 1 divided by this gives us our frequency in hertz, 500 hertz as desired. I'm going to switch to channel 2, which is already done here, and now I have a waveform for my voltage drop across the second resistor. So to measure the voltage peak to peak, I may vertically adjust my waveform to the bottom of the window, center it with the horizontal shift so that the peak is along my measuring axis, and then I can count divisions and multiply by the voltage per division. So I have a fractional or decimal number of divisions, 1 square, 2 square, 3 squares, and then it looks like I have 4/5 of a square. So 3 and 4/5 is 3.8, and then my vertical scale is 2 volts per division. So I may do a old school measurement, 3.8 divisions times 2 volts per division gives me a peak-to-peak voltage drop across resistor 2 of 7.6 volts peak to peak. The multimeter provides a measurement of the root mean square voltage, which across voltage drop across resistor 2 we're measuring 2.5 volts root mean square. My 7.6 volts peak to peak divided by 2 gives my peak voltage, and then multiplying by 0.707 I have the root mean square measurement, which is close to the measured value. Since our measurement is old school, we expect small error. On channel 2, which measures voltage drop across resistor 2, and I'm interested in the period and the frequency of the voltage. So I may vertically adjust my waveform so that the 0 is zeroed, and then I have a horizontal position so that I might see where it crosses from negative to positive, and count divisions, old school. 1, 2, 3. As before, we see 10 divisions left to right, and the unit for the x-axis is 200 microseconds. So old school calculation, we have 10 divisions, each division worth 200 microseconds, and micro is a prefix in 10 to the negative 6.
Yep.
And so this gives us our period in seconds, which is 2 milliseconds. If I take 1 over this, to the negative 1 power, I have the frequency in hertz, which is 500 hertz.
All right, now we're going to take the same measurements using the new school method, which is using the built-in calculator functions of the oscilloscope. First things we're going to do is measure the voltage peak to peak in RMS. So first I press measure, voltage, and select voltage peak to peak, VPP. Further, I'll go to voltage and select voltage RMS. Now it's important to remember that the oscilloscope itself can't actually measure the voltage RMS. That's the job of the multimeter. Instead it derives it from the measurement of the voltage peak to peak. Alright, so as you can see we've got 9.6 volts peak to peak, an RMS of 3.32, which is pretty close to our ideal. Now, we're going to measure the period and the frequency. So first the period, that's already on the top of the menu, as well as the frequency. So as you can see, we have a frequency of roughly 0.000 milliseconds, which is consistent with what we had on our Multisim. And our frequency, it wavers a little bit, but it's roughly 500 hertz, which is perfect. The same measurements, but on channel 2. So I'm going to switch off channel 1 on channel 2, and I'm going to press measure. Now I need to change my source here to channel 2, and I'm going to do the same measurements. So we've got the voltage peak to peak, as well as the voltage root mean square, VRMS. And as you can see, we've got 7.2 volts peak to peak across resistor 2, and the RMS of 2.51, which our multimeter, desktop multimeter said it was 2.5, so that works. Next, we are going to measure the time, both the period as well as the frequency. And you should see something familiar, 2.000 milliseconds, and the frequency of 500 hertz, which is correct.